Alright, this is the last section we're going to cover in this class. So this is the last set of material, and so we are going back to Chapter 5, which Chapter 5 is on integration, which is just a fancy term for finding the antiderivative. Alright, and it's literal. Alright, it's working backwards, given a derivative, a rate of change function. What we're going to do in this chapter is work backwards to find the original function, or applications of an exact change in a function. Integration is also used first. Alright, so first, rules of antiderivatives. And as it turns out, there's not as many rules for antiderivatives as there are for derivatives, at least in this class. Alright, so function, capital, and we usually do antiderivatives with capitals. There's just the rule of thumb that we do. That's the notation that's typically utilized for antiderivatives. Alright, so capital F of x is an antiderivative of some lowercase f of x over an interval, usually its domain, if, when we take the derivative of the antiderivative, it equals that original expression. And so remember, the original expression is the derivative. And we want to know what function gives us that derivative. And so I've got two examples here. Alright, this is my original function, or this is the function that I'm given. Alright, and what I want to find is, well, I want to find the antiderivative, the capital G of x. So when I take the derivative of the capital G of x, it equals that lowercase g of x. So it equals 2x. Well, can you think of the function? When I take its derivative, it comes out 2x. Alright, and this one should be a fairly straightforward one. We'll get to rules later on. But x squared, right, it satisfies that definition. If I take the derivative of x squared, I get 2x. Well, is that the only function that gives us out that derivative? And the answer to that is no. What about the function x squared plus 3? Right, it satisfies that. Or the function x squared minus 100. Right, when I take the derivative of x squared minus 100, I get 2x. And so what there's infinitely many. Right, I can tack on any constant and I get out the derivative that I'm looking for. Alright, and that's going to lead us to our next theorem. Now before we get there, I'm going to do g of x. So again, what I want to find is I want to find the antiderivative of h of x. So I want to find a capital H of x, the antiderivative, so that when I take the derivative of my antiderivative, my h of x, it gives me out my function I'm given, which is 2e to the x. So what function, when I take its derivative, do I get 2e to the x? Well, 2e to the x's derivative is itself, right? 2e to the x. When I take the derivative of 2e to the x, I get 2e to the x. That's not the only one that has that, right? I can tack on any constant I want, right? If I have 2e to the x plus 40, right? That's also an antiderivative of that expression. Or 2e to the x minus pi, also an antiderivative. And so there are infinitely many outcomes that I can find. And so that leads me to the next theorem that we're going to look at for antiderivatives. Alright, so let capital G be any antiderivative of the function lowercase f of x. C is a constant. Alright, constant just means it's a real number value. Then every antiderivative of f of x must be of the form capital F of x equals g of x plus some c. Alright, this is a function that's called the family of antiderivatives. And what that means is that it's all possible antiderivatives of my function. And using the examples I had above, I remember the g of x was 2x, and so the family of antiderivatives for that was x squared plus c, meaning c can be anything, and so there are infinitely many values c can be, and so this is all possible antiderivatives. When I take the derivative, I get that g of x back, right? I take the derivative of this, I get 2 of x back because the c will zero out. Same thing's true for the other one, right? H of x, I'll do lowercase first. My lowercase h of x was 2e to the x, right? That was the function I was given. The antiderivative of that function, well, is 2e to the x plus some unknown constant, right? When I take the derivative of that, I get back to the expression I was given. Where c can be anything, right? It's the family, so there are infinitely many possibilities. There's infinitely many functions that have that derivative. That's what this theorem is stating. This function is the derivative of infinitely many functions because I can tack on any constant I want from infinity to negative infinity, right? And so that c is important, and you have to remember to add it. All right, so some notation that we use. So again, math, it's a language. We use our own symbols and our own notation. And so for antiderivatives, just like we call the sum of two numbers addition, all right, the multiplication of two numbers a product, the division of two numbers a quotient. Well, when we're finding the antiderivative, and we want to find the family of antiderivatives, we give it its own name and its own notation. All right, the name is called the indefinite integral. All right, integration is the process where we find the antiderivative. All right, the indefinite integral represents the function that finds the family of all antiderivatives, all possible antiderivatives of my given expression. Right, what's kind of nice about these is you can kind of always check your answers, right? My indefinite integral, when I take its derivative, always has to be equal to the function I'm given. Alright, so again, the lowercase function is what I am given. That's the function I'm provided. I want to find its antiderivative, and so that's what's going inside my integral symbol. Alright, so this is the notation. Alright, so this is my capital F of x. This is all possible antiderivatives of lowercase f of x. This lowercase f of x is what's inside. Alright, g of x is usually what's considered the general antiderivative without a constant. And then c is just the constant. And that c is important. You can't leave it off. 0 is one possibility, right? Constant of 0. So if you leave c off, you found one antiderivative. So you have to make sure to always tack on a c, because I don't want one antiderivative. I want all possible antiderivatives. And so you have to remember that plus c. It's really easy to forget that, but it's vital. It's very, very important, right? Infinite versus 1 is very different, right? The plus c means there's infinitely many possibilities. Without the c, I just found one of the infinitely many possibilities. All right, this is called the this sort of S-like shape. It is an elongated S-like shape. And again, it comes from, we'll get to the fundamental theorem of calculus. It does represent something in terms of a sum. But it's called the integral symbol. All right, so this is the integration of f of x. The dx represents with respect to what variable, right? When I took the derivative, it was respect to d of x. Well, I'm undoing the derivative, right? I'm working backwards. Well, I'm undoing that change in x, right? And so that's the variable part, right? I'm antiderivative with respect to x, right? X is the variable part. All right, you can always check your answer by taking the derivative of your answer. It should, again, although kind of usually just do a mental check, all right? But you can always do this. What's kind of nice about this, does the answer you're giving me make sense? All right, is my antiderivative really my antiderivative? We'll do a quick mental check that that's the case, right? When I take the derivative of my answer, I should get back that function that's inside my integral. Alright, so now we're going to go over the rules. The rules for integration, the rules for finding the antiderivatives. And remember, you always have to tack on c, because I want the family, right? All possible antiderivatives. You do have to remember that c, so don't forget it. Alright, if you don't have the constant, right, like I said, you found 1, the general antiderivative. I don't want 1, I want all infinite. Alright, so the first rule, the constant rule. So k represents some k, some number between infinity and negative infinity. And remember, this is the differential equation, right? That's what that is. That's the derivative. I want to undo the derivative. Antiderivative is what I'm looking for. Well, what function just gives me a constant? Well, it's the constant times the variable that does that. So it's k times the x variable, and then there's some unknown constant that I could tack on because I could have had a simple linear equation. All right, an example would have been 10 dx, right? The family of antiderivatives for 10 dx? Well, this was the derivative. Alright, so 10 times x plus some constant. That would be my family of antiderivatives. If I take the derivative of this, I do get back to this 10 inside, right? The derivative of 10x is 10. Constant always zeroes out. Alright, so that's what I meant. You can always do sort of a quick mental check. Does my answer make sense? When I take the function's derivative, do I get back to my original expression? And I do. And usually, like I said, it's a mental check. But you can always do that. Alright, the power rule. Alright, when we're taking derivatives, the power rule comes into play a lot. Well, antiderivatives, you also have a power rule. Alright, so remember, antiderivatives are working backwards. I'm undoing the derivative. So I've got to do the exact opposite in the opposite order. So the original derivative would have been I pull my power and multiply by it, pull it up front, multiply by it, and subtract 1 from my exponent. Doing the antiderivative, I undo that, so I do the exact opposite. My first step is to add 1 to my power, right, undoing the subtraction, and instead of multiplying, I do the opposite of multiplying, I divide by it, but I divide by the plus 1 power, alright, so it'd be my x raised to 1 power more, 1 degree more, divided by whatever that degree is. Alright, and then there's a constant at the end because, again, I need the whole family of antiderivatives. Right, and so there's my power rule. I add 1 to my power, and instead of multiplying, I divide. And you've got to remember that because these are antiderivatives. I'm undoing the derivative, so I've got to work backwards. Alright, so a simple example, actually I'm probably going to do a couple, because sometimes we do have to manipulate these. Alright, now a quick note, my power can't be -1. We'll talk about why in a little bit. So this can be anything but -1. Alright, it can't be -1. Alright, I'll explain why when we get to another rule later on. Alright, so I'm going to do a few examples. So my first example, I'm just going to do a simple case. X raised to the 5th degree with respect to x. Alright, I want to find my family of antiderivatives. Well, I use this rule. I take x and raise to 1 more, add 1 to it, so I get 6. Instead of multiplying by 6, I divide by 6. Right? And so my family of antiderivatives would have been x to the 6 divided by 6 plus c. The check is, when I take the derivative of this, I should get x to the 5th out, and I do. Right? This is, again, just the check step. This is my answer. So this is usually, again, a mental step. We need to divide by 6 because when I take the derivative of this, I'd pull the 6 out, and so I'd have to have that divide by 6 to cancel that. And then we 1 degree less, which would give me my 5, so it does check. Alright, so that's my antiderivative. Alright, so I am going to do a couple more examples because just like with the derivatives, sometimes I have to manipulate my function to get what I want, right? For example, suppose I had the square root of t, and so my variables with respect to t. Well, just like with the derivative, I can't take the antiderivative of the square root of t. I have to take it t raised to the 1/2. Same thing has to happen here with antiderivatives. Right, then I can use my rules to find my family of antiderivative. I add 1, right? Antiderivatives add 1. So I take 1/2 plus 1, so I'm going to get 3/2. And then we divide by that, and I'm going to talk about this in a second, and then tack on a constant. Now, this is improper, right? It's an improper fraction to divide by a fraction. And so remember, division by a fraction is the same as multiply by the reciprocal. So we actually usually skip this step and write the reciprocal. The reciprocal of 3/2 is 2/3. T raised to the 3/2 plus my constant. And so this is the family of antiderivatives that I'm looking for. Right? And you do a quick mental check. I need the reciprocal because if I took the derivative of this, well, I'd pull out my 3/2 here. The reciprocal would means they'd cancel each other out, leave me with 1, which is what I want because there's a 1 in front of my t to the 1/2. Subtract 1 from this, and then I'd be left with my 1/2 up here, so it does check. Alright, well, I'm going to do one more example. Again, I'm just going to erase it and do it here. Alright, so again, the other thing that we can manipulate is when we have a simple division. All right, as it turns out, there is no quotient rule for antiderivatives, even though we do have a quotient rule for derivatives. We will not have a quotient rule for antiderivatives. It doesn't exist for us. All right, there are special cases where we can work with them, but only in special cases. So suppose I have 1 over y cubed, so my antiderivative would be with respect to y. Well, just like when we did the power rule, all right, I have to change that. All right, I change that. Instead of 1 divided by y cubed, I change it to y to the negative 3, and again, taking the antiderivative with respect to y. Now I can use my antiderivative rule. All right, to find my family of antiderivatives, I use my power rule, which means I add 1. I'm adding 1. All right, add 1 to my power, so negative 3 plus 1 is going to give me a negative 2, and then I divide by that. All right, which, like I said, it's fine if you leave it like that. Just be aware of, though, if this was a problem on Connect, they would rewrite it. All right, so it does rewrite as 1 over negative 2y squared. But I would accept on your test either one of these. All right, so there's the undoing the power rule, antiderivative of the power rule. All right, a constant multiplier. So it means k is some number times my variable part, my function part. And so just like with the derivative, I can pull that constant outside of my integral. Right, because I only want to find the antiderivative of the function part. We did the same thing with derivatives. The constant multiplier always comes along. I take the derivative of the variable part. Well, same thing here. When I do antiderivatives, the constant multiplier comes along, I just take the antiderivative of the variable part. All right, so an example would be something like 12t to the third. Again, the derivative with respect to antiderivative with respect to t. The 12 is just going to come along. It's a constant multiplier. That's the function part. So I take the antiderivative of the function part. I'm going to rewrite it just to show you this is what we're doing, although we usually just know this is happening and we don't rewrite it. Alright, but this is basically the idea here. 12 is going to come along. I could pull 12 out. I'm only taking the antiderivative of the variable part. Alright, like I said, this is usually a mental step. We just know that's happening. We know 12 is going to come along. I use my power rule on the t cubed, which is going to be add 1, divide by, and I've got my unknown constant. And so the family of antiderivatives, when I simplify, because I can take 4 and divide it into 12, is going to be 3t to the fourth plus c. And a quick check is, if I took the derivative of that, I would get back to my original function up here. Right? Because I took the derivative of this, I take 4 times 3, that would give me my 12. And 1 degree less would give me my 3, and so it does check. Alright, sum and difference rule. Just like with the derivative, I can split my integration over my individual functions. Again, just at the little individual parts. So this allows me to take care of more complex functions like a polynomial. Alright, so again, I'm not going to rewrite the symbols, although technically that is what you're doing. You would rewrite it. Maybe I will just to show you. I'm taking the antiderivative of each individual part. Alright? But usually this is a mental step. Alright, I know that's what I'm doing. I'm doing the antiderivative of each individual function and then adding and subtracting accordingly. Alright, so the 10x to the fourth, well, the 10 is just a constant multiplier. It comes along. And then I'd add 1, so I get 5. Divide by that 5. Alright, done with the first one. Now in the next term, I've got 4x squared. So I add 1, make it cube. Divide by 3. And then the last one's my constant rule, 3 times x. And then don't forget, I want all of them, so there's a plus c at the end. Alright, this will simplify, and you should always write your answer with your fractions reduced. So 10 divided by 5 is 2, x to the fifth. That fraction doesn't. So it stays 4/3 x cubed minus 3x plus c. If you took the derivative of this function, it would equal the function inside. You could do a quick mental check, right? The derivative of 2x to the fifth is 10x to the fourth. The derivative of 4/3 x cubed, well, when I took the derivative, the reason why I needed to divide by 3 is because when I pulled the 3 out, I needed to cancel with this 3. And then 1 degree less is going to leave me with a 2. And then the antiderivative of negative 3x is negative 3, and the constant always zeroes out. Alright, the exponential functions. There are two of them here. They are different. So this is when it's just e to the x. Alright, all by itself. So the antiderivative of e to the x, well, it's the same as the derivative of e to the x. It's itself, right? E to the x plus some unknown constant. So the family of antiderivatives would be itself plus some constant. Alright, this other one, though, this would be when I have a k inside. So this would be exponential growth or exponential decay. If k is positive, it would be growth. If it's negative, it would be decay. Remember, when we did that derivative, it was itself times that k. Well, the antiderivative is the opposite of that. It's itself. Instead of times this k, it's divided by that k. Alright, because I've got to undo the multiplication of it. And so I am going to do an example of this case. So suppose that I had 10e to the 2x. Alright, and so the antiderivative of that would be itself, 10e to the 2x, but I'm not done yet because of the 2. I've got to divide by that 2, and then there's the unknown constant at the end. And so simplifying it, it would come out 5e to the 2x plus c. And to make sure you've done it right, remember, this is a derivative. This function, when I take its derivative, should give me 10e to the 2x. And so if I forgot to divide by this 2, I wouldn't get the right answer because I would have had 10e to the 2x, and when I took the derivative of it, it would have been 10e to the 2x times 2, which is 20. And so I've got to remember that this is what we want, right? So I've got to divide out that 2 we would have multiplied by. All right, and there's my function. All right, the last rule that we're going to talk about. Now, there's going to be one more rule. It's in the next section. Undoing the chain rule, and that's it. We don't have a quotient rule, and we don't, there's technically a product rule, but we're not going to go over the product rule. All right, we are going to do the chain rule. That will be the last rule that we're going to do in this class. All right, so that's in the next section. Now, all right, this is the last rule from 5.1. All right, so 5.1. So remember I said earlier when I did the power rule, I can't use the power rule when I'm raised to the -1 power. And again, the reason why is because if I try to use my power rule, right, my power rule is I add 1. Well, if I add 1 to my -1, I get 0, and then I'd have to try to divide by 0. Well, I can't, right? There's an error. Well, remember, this really means 1 over x, right? X to the -1 means 1 over x. This is a derivative. All right, what function finds the derivative, or gives the derivative, (1 over x, right? It's our special natural log. All right, so it's the natural log of x plus some constant if x is greater than 0. And instead of writing this every time, because that's true, my original function inside the integral could be positive or negative, right? And so when I get my natural log, though, I can't have negatives. And so either you have to write, this is the antiderivative so long as x is positive, or the way we actually get around that is instead of writing that, we do an absolute value of x and then we're safe. And so what you really want to do is when you have the integration of 1 over x dx, you want to write the natural log of the absolute value of x plus c. If you don't do the absolute value, then you have to include that statement. All right, so again, we usually just do this to make it simpler. All right, so an example would be, suppose I had 3 over x. All right, well, 3 is just a constant, right? If I wanted to, I could pull that 3 outside, and I'm left with 1 over x. And so it's going to be 3 times the natural log again absolute value of x, because I don't want to have to write the if x is positive statement. And so there would be my family of antiderivatives that would work. 3 times the natural log of the absolute value of x plus c. Alright, so let's finish this up. The introduction to antiderivatives. In the next set of notes, we're going to be practicing them and mixing them together. Alright, and so we'll do that in the next set of notes. Alright, so we'll stop 5.1 part 1 there.